to section 15.6, which is kind of a theoretical but interesting section about change of variables. It's going to focus on just general changes of variables today. And then after Thanksgiving, the next Monday a little bit too. We will then go backwards through chapter 15, back to section 15.3 and 15.4, I believe, to focus on triple integrals, though we'll focus on triple integrals in the context of relatively simple examples. That sounds like kind of a scary topic, but if we do relatively simple examples, I think it won't be so bad. And we'll use cylindrical and spherical coordinates as well. But I want to motivate our main topic for today by considering integration over a parallelogram of a particular density function. I'll write this function down on the board here. So rho, again, is a common letter people use for density. So I'm starting to be like the book here and use rho as my density function. And again, we could imagine this being a thin plate, a thin sheet of metal. Actually, this has kind of a fun name. Remember how nabla is kind of the fun name for the gradient operator, also called del. Thin sheets of metal have fun names as well. They're sometimes called laminas. Let's see, let's create a lamina that's going to be a parallelogram in shape. Let's make this be the point 5, 1. Let's then go up to the point 7, 7. Try to make this reasonably accurate. Right about there. Something seems not so good about that. I'll go with it here. 7, 7. Let's pretend that's the point 7, 7. If I'm going to make a parallelogram, let's make the origin a third point here. I'm going to need to make a fourth point that's effectively got a position vector that's the same as this vector that goes from 5, 5 to 7, 7. The displacement vector from 5, 1 to 7, 7 is going to have components 2, 6, right? Subtract the coordinates. 7 minus 5 is 2, 7 minus 1 is 6. 2, 6, right about here is going to be the fourth point for my parallelogram. It's not perfect. Good enough here. Pretend that's a parallelogram. It's hard to draw a board. Maybe I move this over a little bit. Looks pretty good? All right, so that's our region of integration. That's our domain that we're considering. That's the thin sheet of metal. We'd like to find its mass. Again, conceptually, you can write this down as a conceptual equation. Integrate the density to find mass. Imagine this being in grams per square centimeter. For this lamina, here's how you spell lamina. Grams per square centimeters, you can imagine dA as being in square centimeters. You can imagine this as a multiplication to give you a little tiny mass of a little tiny chunk of this. You can call it dm if you wanted to. And you can imagine that the integration is adding up those little tiny masses to get the total mass. And it's just an imagination tool. How are we going to calculate this, though? Is this vertically simple? Is it horizontally simple? Neither? Both? What do you think? Thoughts about that? What if I draw lines like this? Does that help? You can think of it as vertically simple, actually, and horizontally simple as well. You can think of it as the region between the graphs of two functions of x or y. However, they would be piecewise functions. Focus on being vertically simple. This domain is the region between the graph of this function that goes like this and this function that's piecewise in this way. So you'd have to use piecewise formulas. Is there a way around that? We are going to ultimately come to a way around that. But for the moment, let's instead break the region itself up into pieces. Consider a vertical line down from this corner right there and a vertical line up from this one right there. And I've broken the region up into 3 pieces, each of which has a fairly simple lower function and upper function. Here and here, here and here, and here and here. I'm going to need the equations of those line segments to determine the lower and upper functions in each case. These two go through the origin, so their equations are going to be the simplest. The slope of this one is 1/5, so it's y equals 1/5 x. Yep, it goes through the origin, so the y-intercept is 0. This one's got a slope of 6 divided by 2. It's got a slope of 3. Y equals 3x. These other two, though, don't go through the origin, but their slopes are the same. This one's got a slope of 3. It also goes to the point 5,1. A quick way you can now write down the equation to make sure that happens is like that. That's essentially point slope form. The one on the other side right away, though. You might want to double check, does it go through this point too? Just plug in x equals 7 there. 7 minus 5 is 2, times 3 is 6, plus 1 is 7. It is going through that point. Expand it to simplify it a bit. 3x minus 15 plus 1 is minus 14. And now go up here. This one's got the same slope as this one, 1/5. Y equals 1/5. This point is 6, 2, so we could do an x minus 6 plus 2. Check that goes through 7, 7. 7 minus 6 is 1. Oops, let's see. Got the wrong thing there, sorry. 2, 6. There we go. 7 minus 2 is 5. 1/5 times 5 is 1. Plus 6 is 7. Okay, so let's write down how to calculate this integral using these 3 pieces. You need 3 integrals. These pieces are only overlapping along these boundaries that are one-dimensional and don't have any area to them. And so you can find the total integral of this function over the entire domain by integrating over each subdomain and adding the results. In each case, let's write each of those integrals as an iterated integral with respect to this vertically simple decomposition. So x is going to be the outer integral when you do that. And in this case, well, in that kind of case, x needs to go between 2 constant values. In the first integral, x will go from 0 to 2. And then for each x between 0 and 2, y goes between 2 functions of x. That function and this function. X over 5 to 3x. The row I'm picking again is x times y squared plus 1. I'll go ahead and write that in there. dy dx is the way to do it for vertically simple. That's just the integral over the first piece. Now I do the middle piece. X now goes between 2 and 5. And for each x between 2 and 5, y goes between these 2 functions. Y equals x over 5, and y equals this, which I'll write as 1/5 x. Let's see, 6 as a fraction over 5 is 30/5. Minus 2/5 is plus 28/5. I think I'll actually write it as x plus 28 over 5 to save time for the typing. X plus 28 over 5. Once again, oops, forgot the lower limit, x over 5. Once again, same function, xy squared plus 1, dy dx. Last integral. Over this last piece, x goes from 5 to 7. That's my problem, I put 7 too far away. Making my picture. So yeah, x goes from 5 to 7, y goes between these 2 graphs. This one is 3x minus 14. This one up here, once again, is x plus 28 over 5. X minus 14 down here, x plus 28 all over 5 up there. X times y squared plus 1 is the function we're integrating. There we go. Those three integrals added together should give you the right answer. I'm not going to take the time to do all three integrals. I think I'll take the time to do the inner integral of this one by hand. We'll see that's the easiest one to do. The x plus 28 over 5, and the fact that you're going to get a y cubed when you do the inner integral is going to make these two take more time than it's worth. But let's look at that first integral. The outer integral is x going from 0 to 2. Do the inner integral, integrate with respect to y. And here you're going to get a 1/3 xy cubed plus y. Y goes between x over 5 and 3x. It's good to emphasize that it's y that's doing that. Plug in y equals 3x first. Plug it in there, you're going to get 3x cubed, which is going to be 27x cubed, 3x quantity cubed. 27 divided by 3 is 9. You'll get 9. X cubed times x is going to be x to the 4th. Plug in 3x there, you just get plus 3x. Now plug in x over 5 in place of y and subtract what you get when you do that. One-fifth cubed is 1 over 125 times 1/3 is going to be 1 over 375. We're getting x to the 4th again, and then a plus 1/5 x, etc. Okay, you can do that now. Let's see what the answer is going to be. In fact, let's guess the answer ahead of time. This is always good to do. Make a real round guess of what the answer might be by making a contour plot of the function and trying, based on that contour plot, to guess the average value of the function. If I just type it like this, that's not going to give me the right kind of picture. Why not? What's this going to make? It's going to make a contour plot over a square. X and y both going between 0 and 7. Let's add more contours. If I want to restrict the domain, I need to add that region function option. Region function, arrow function. And what goes in here? Let's see, this is a restriction in the xy plane, so I need an xy, no z there. Then you put a comma, and then you put your conditions on x and y that are going to generate the domain that you want. In order to help me figure out what to put there, it's best to take these equations and write them so that x and y are both on one side and a constant is on the other side. So this equation, for example, is equivalent to 3x minus y equaling 0. And this equation right here, y equals 3x minus 14, that's equivalent to 3x minus y equaling 14. So 3x minus y is a quantity in this parallelogram that must vary between 0 and 14. The same kind of thing with this equation and this one up here, and maybe multiply everything by 5 as well. It's kind of a mess here. That equation is equivalent to x minus 5y equals 0. Multiply both sides by 5 first, and then subtract 5y. Up here, multiply everything by 5 first, and maybe subtract y, and also subtract 28 times 5. 40 for both sides. multiply everything there by 5. 5y, oh no, the 5 cancels, excuse me, equals x plus 28. That's equivalent to x minus 5y equaling negative 28. So that quantity, x minus 5y, varies between negative 28 and 0. So I'm going to use those facts within this region function option over here. I'll put both sets of inequalities. And double ampersand is the way Mathematica uses, is an and operator to make sure both conditions are true. So we have, again, looking at what I circled over there, 3x minus y is between 0 and 14. If you want to get a less than or equal to in there, you just type less than and then equal to, and then once you start typing the next thing, it morphs into a less than or equal to sign. Watch it here, 1, 2, 3, go, like that. Again, double ampersand is the and operator. I want not only those inequalities to be true, but also the other inequalities to be true. That x minus 5y is between negative 28 and 0. And there we have it. There's our parallelogram. What's the average density? Well, just looking at the formula here, I see that the density at the origin is going to be 1 gram per square centimeter. But you don't see any contours down there. Maybe we should turn the lights off here for the moment. I'll turn it back on in just a minute. Is that too dark? Did it adjust okay? All right. The function's not changing very much here. The density is fairly low and close to constant. It's not changing very rapidly here because these level curves are far apart. As you keep going up, though, these level curves get closer together, and the function values start going up pretty rapidly. Now you're in the hundreds. Up here, you're about 200, and you're finally about 300. Upper right corner there, perhaps around 340 or something, is the value of the function, 350. I guess we can do row of 7, 7 to find it out. Row of 7, 7. In the upper right corner, the density is 344 grams per square centimeter. So what's the average value? Well, the vast majority of the parallelogram has densities that are in the lower region. It's these lighter shades that are higher. A large chunk is in the lower values, probably under 100. In the last class, I guessed that the average density, I said, oh, it's probably 50, 60, 70, 80, something like that. Okay, now I know what happened. The average density ends up being, I think it was around 68 or so. So our estimate based on that, if we guess 68 for the average density, our estimate for the value of the total mass should then be that average density in grams per square centimeter times the entire area in square centimeters of this parallelogram. You've figured out areas of parallelograms before in this class in a nice way. Do you remember there being a graded assignment? Oh, at least a month, maybe a month and a half ago, about finding areas of parallelograms. It's in the section about cross products, section 12.4, page 698. There's a picture right there for it. Remember doing that problem? I'm going to use that fact here. If you draw two vectors based at the origin and having tips at the point 5,1 and the point 2,6, those vectors span this parallelogram. That's the language you use. And if you put those vectors, the components, in a matrix, and take the determinant of that matrix, you're going to get plus or minus the area of this parallelogram. If you take its absolute value, you will actually get the actual area. So take the absolute value of the determinant of the matrix formed, again, by taking these two position vectors, 5, 1, and 2, 6, 6 and putting them in the rows of this matrix. 5 times 6 is 30, 2 times 1 is 2. The answer is 28 for the area of this parallelogram. So therefore, again, my estimate for the value of the integral is going to be about 68 times 28. Again, that 68 was just what I think I remember from the last class period as being the answer, close to the answer. I think it's a little smaller than that. I think the answer for the integral ends up being a little smaller than this. Maybe my guessing is wrong. Maybe it was more like 65. My memory might be faulty. It might be 65. Okay, let's do the integral now. Type this in as fast as I can. Use some copy and paste magic here to help type it in faster. There's the first integral. Copy, paste with plus signs, and make appropriate adjustments. Make this now go from 2 to 5. And look at the picture. We still have an x over 5 down here, but now up here we have a that's the x plus 28 over 5. That's the thing, again, if you try to do the middle and ending integrals by hand, you'd have to cube that thing. That would get in place of y, and you have a y cubed, and you have to cube this. So it would be quite a pain to do by hand. Over here, let's see, x goes from 5 to 7. Y goes from 3x minus 14. Once again, up to x plus 28 over 5. Did you get everything right? Where are you saying?
5 to 7.
5 to 7. Is that the only mistake? So I know for sure this is something between 1,500 and 2,000. My memory must be faulty, I think, about the average value. 1808.33 is the value of the integral, approximately. Actually, exactly, it would be 0.3 repeating. Therefore, if I divide that by 28, the area of the parallelogram, then I'll get the average value, the average density. The average density is closer to 65, not 68. Okay? All right, so that's, based on the tools we have so far, that's how you'd have to do that integral. Now I'm going to show you an alternative way to doing the integral that is better in some respects and harder in other respects. Overall, I think the effort is worth it, though. What I'm going to do is I'm going to change variable, essentially. I'm going to do substitution. But since I have two variables, an x and a y, I need two new variables for my substitution. We've done it already. R and theta, polar coordinates, are substitutions. But now I want to do a more general substitution. I'm going to use the letters u and v. Those are the most common letters to use here. The question is, what should u and v be? And based on the nature of this parallelogram, how we described it as 3x minus y going between 0 and 14, and where'd it go? X minus 5y going between negative 28 and 0. That gives me a hint that probably u should equal 3x minus y, and v should equal x minus 5y, so that u and v go between constants. Let u equal 3x minus y and v equal x minus 5y. If I make those substitutions based on how I described the parallelogram, u will go between 0 and 14, v will go between negative 28 and 0. In terms of u and v, in terms of what's really an alternative coordinate system, that has a u-axis looking like that, and a v-axis that's not at a 90-degree angle with u. Looks like this. In terms of a new coordinate system with slanted axes like this, essentially this parallelogram becomes a rectangle somehow in that coordinate system. You can describe it in set builder notation based on assuming you got that new coordinate system as u going between 0 and 14 and v going between -28 and 0, which in a UV plane that you would draw the normal way would look like a rectangle. In this plane, you'd imagine as sort of being a slanted rectangle. The parallelogram is like a slanted rectangle. But that, again, is going to make our limits of integration be nice. 0 to 14 and -28 to 0, constants. We do pay a little bit of a price, though. The formula for the density becomes more complicated. We essentially have to get rho in terms of u and v, which means we need to do a little algebra here. We need to solve for x and y in terms of u and v. It's not too bad here. You can solve this equation first for y in terms of u and x. Y will equal 3x minus u. Then if you substitute that into the second equation in place of the y, you'll get an equation that just involves v and x. And u, I guess, that you can solve for x in terms of u and v. Does that make sense? If you substitute that in there, you'll get an equation involving v, u, and x. And you could solve that equation for x in terms of u and v, and you're halfway to your answer. So go ahead and do that. Substitute. Catch if I make any mistakes here. X minus 15x, that'll be negative 14x. And then we have a plus 5u. Minus 14x plus 5u. That equals v. Solve that for x. When you do that in your head, x is going to equal 5u minus v over 14, it looks like to me. Swing the negative 14x to the right as a positive 14x. Subtract v, and then divide by 14. Now take that and substitute it back up here in place of x, so that you get y in terms of u and v. And that'll be the last thing we have to do here. X is 3 times 5u minus v over 14 minus u. This is what y equals. Simplify that. For the u, you're going to get 3 times 5 is 15. 15 14ths u. Minus 1 times u is 1 14th u. And for v, you're going to get negative 3v over 14. Looks to me like you can write this as u minus 3v over 14. I have to take these two things now and plug them into rho, which is not super pleasant, but it's not super unpleasant either, although the final answer does end up being more complicated than I expected. If you just type it like this, x is 5u minus v over 14, y is u minus 3v over 14, the answer comes out unexpanded, like that. So we would want to expand it. There we go, it's more complicated than I expected. What do you think? Do you think if we integrate this function, where u goes from 0 to 14 and v goes from negative 28 to 0, do you think we're going to get the right answer? Got a guess? You might be thinking, well, isn't that what I've been trying to do the entire time? Let's try it here. U goes from 0 to 14. V goes from negative 28 to 0. Again, I could switch the order of integration as I'm doing it here now. The inner integral is going to be dE, the outer integral is going to be du. I'll just copy and paste this in here. Is that going to be the right answer or not? Think back to what you do in first year of calculus with substitutions like u equals 5x. Do you just substitute that into the, if you've got a situation like this, well, let's make it a little bit more complicated. 5x plus 4. Say you were trying to integrate square root of 5x plus 4 by doing this substitution. Do you just integrate square root of u? You'd have to change limits of integration if you had limits of integration, but also du is 5 dx. You don't just replace the dx with a du. You replace it by a 1/5 du. You've got to make sort of some kind of adjustment there for the fact that this equation is a linear function of x that's got a slope that's different from 1, that's amounting to doing some stretching on the x variable to get the u variable. You do have to do something similar here. This is not going to be the right answer. That is not the same as this. However, with this particular example, I do claim that it's a nice multiple of this. I claim it's that thing times 1/14, or divided by 14. Oops. Copy. I want to do this one. There we go. In the last class, I calculated that 1/14 in my head, though I initially got it wrong. I initially thought I had to multiply by 14 instead of dividing by 14. That's division by 14. But how did I calculate it, not even in my head at all? What I did was I calculated a determinant of a certain matrix in my head. What matrix? It's called the Jacobian matrix. And the determinant that I calculated is called the Jacobian determinant. Notationally, it's kind of odd. You write dA based on these new coordinates, u and v, as follows. This is kind of strange. Okay, just deal with the strangeness here. It's a certain multiple of dx dy. The multiple is written like this. Absolute value of a strange-looking symbol. There's the strange-looking symbol. It looks kind of like some odd sort of partial derivative. Is it? Well, no. But it's related to some partial derivatives. This is called the Jacobian determinant. Of this substitution or of this transformation. Also in our book they call it JAC, J-A-C, for Jacobian. I'm going to leave that blank for the moment. What determinant is it? It's the determinant of what's called the Jacobian matrix. It's a matrix of first order partial derivatives. Partial of x with respect to u, partial of x with respect to v, partial of y with respect to u, and partial of y with respect to v. The book uses the absolute value notation for the determinant, but that's a little bit misleading because determinants can be negative. So I'm avoiding that here. I'm just writing det. Multiply what's on the main diagonals here, dx du times dy dv. Subtract the product of the entries on the off diagonal, dx dd times dy du. That could be a negative quantity. It is in general a function of u and v, although for this example it's constant. And in fact the constant is 1/14. You need to take the absolute value of that quantity, so that dA is positive, so to speak. imagine differentials in this case being to be positive because they represent areas. Let's confirm that this does give you the right answer here. Look at these two equations. Partial of x with respect to u is going to be 5/14. dx dv is going to be negative 1/14. Based on this one, dy du is 1/14, and dy dv is negative 3/14. The Jacobian matrix, again, this is called the Jacobian matrix. It is different than the Hessian matrix. The Hessian matrix was a matrix of second order partial derivatives for a function f whose domain was either R2 or R3 and whose codomain was just R. This Jacobian matrix is a matrix of first order partial derivatives for a transformation, essentially. A couple equations, these two equations define a transformation really from the plane to itself, from a UV plane to an XY plane. These two equations together can be thought of as a function that takes points in a UV plane, a two-dimensional plane, two-dimensional points in an XY plane. It's a different kind of function. Consider all the possible partial derivatives there, put them in a matrix like that. It's called the Jacobian matrix of the transformation. And in this case, it's going to equal the determinant of the matrix whose entries are 5/14, negative 1/14. Then down here we have 1/14 times negative 3/14. This gives you negative 15/14 minus negative 1/14. Oops, forgot to square the 14s. That's going to give you negative 14 over 14 squared, which is negative 1/14. And then the absolute value of that is going to be positive 1/14. That's why I need the extra 1/14. To get the right answer, I need to divide by 14. Not explaining why this works, okay? As is often the case in this class, you're just trusting me here. The book does try to explain it. If you want to understand what's going on here, you should study the book, section 15.6. It's kind of a long, difficult section, but I think the benefits definitely are there for you if you put the work into it. Essentially, this Jacobian determinant thing, the absolute value, is kind of like a magnification factor, a local magnification factor. It's not always constant. It's constant in this case. In this case, it's 1/14. In essence, when you use these equations to transform from a UV plane to an XY plane, all the areas get scaled down by a factor of 14. That's essentially what's happening. And let's spend the last bit of time here in class today thinking about what I've just been saying, transformations. By the way, I'm going to add a little bit to this notation here now. I'm going to put a capital G in here. What's the capital G? Capital G is going to be the function essentially defined by these two equations. It's going to be a function whose domain is R2 and whose codomain is R2, or some subset of R2 for the domain. In this case, you can consider the domain to be all of R2. In this case, g of u comma v, look at these two equations, are 5u minus v over 14 for the x coordinate and u minus 3v over 14 for the y coordinate. So this is taking a two-dimensional point described with these new coordinates u and v and giving you a two-dimensional point out. Based on these expressions here, these equal the x and y coordinates of in the original domain. How can this be visualized? Let me visualize it first with polar coordinates, and if we have time, we'll visualize it in this video. Let's visualize what's going on with polar coordinates. Now, usually what's done is you have two separate planes. With polar coordinates, you'd have an r theta plane and an xy plane. And you draw domains, or at least in this case, well, we wouldn't be using the parallelogram here, some sort of domain in this r theta plane, and watch to see what it gets mapped to. in the xy plane. These things are sometimes called mappings, by the way. These transformations are also called mappings. They are functions, so all three words mean the same thing here. But the words transformations and mappings have sort of a geometric flavor to them, and that's why we have to use those words. Let me show you something here, though, with polar coordinates. Let's think about this with polar coordinates. I'm going to use parametric plot in a way I haven't done before. Almost always we've used this to graph parametric curves of some parameter, typically t, or I think sometimes we've used theta. In this case, I'm going to use r and theta as my parameters. I'm going to use two parameters in this case. R times cos theta is going to be the first coordinate, and r times sine theta is going to be the second coordinate. Now, Mathematica doesn't understand what r and theta mean. It doesn't imagine them as being polar coordinates like I am. It is going to graph these points as r and theta vary in an xy plane. That's how we would want to think about it. Let me go ahead and let r and theta vary. Let's let r go from 1 to 2, and theta go from, say, 0 to pi. It's treating those like x and y coordinates. You should realize it's going to graph something that looks like that. Right, so this is the x-axis here. This is the y-axis. Actually, I guess the x-axis is a little higher than there. It's right here. There's the origin right there. R is varying from 1 to 2. That's the distance to the origin. And theta, the angle with the positive x-axis, is varying from 0 to pi. Okay, so you really should have been able to guess that that would be the picture. But now I'm going to do something kind of strange. I'm going to embed this in a manipulate to make an animation of something. I'm going to call my animation parameter lambda, just because that's what I'm used to using. The lambda here is not a Lagrange multiplier, so don't confuse this with Lagrange multipliers. It's also not an eigenvalue, so don't confuse it with eigenvalues. Lambda is just going to be my animation parameter. It's going to go from 0 to 1. What I would like to do is I'd like to create an animation that shows the effect of the coordinate change here with polar coordinates geometrically. In this case, the g of r theta is r cos theta, r sine theta. When you think about r going from 1 to 2 and theta going from 0 to pi in the xy plane, you get this half of a washer. But if you imagine graphing something like this in an r theta plane, you would just get a rectangle. R goes from 1 to 2, theta goes from 0 to pi. It would be a rectangle in a plane labeled with r and theta. To imagine that rectangle getting transformed into this half of a washer, I'm going to use a little trick. I wouldn't expect you to know this trick. Let me explain it a little bit. What do you see here? You see r theta times 1 minus lambda plus r cos theta, r sine theta times lambda. When lambda is 1, which is the last value of lambda, that's 0. This part's not there anymore. That's 1. When lambda is 1, you get the graph of just this thing, which we've already graphed. It's this half of a washer in the xy plane. But what happens when lambda is 0? When lambda is 0, that's 0, and this part goes away. This is 1 minus 0 is 1, and you're just left with this. You're graphing r comma theta as r goes from 1 to 2 and theta goes from 0 to pi. Now again, Mathematica, the symbols are just symbols. They don't necessarily have an implicit meaning. But with parametric plot, it plots things as if they are in rectangular coordinates. So when lambda is 0, it's going to treat this as just a rectangular coordinate plot based on these two parameters. It's going to graph the rectangle, going from 1 to 2 in the horizontal direction and 0 to pi in the vertical direction. There it is. So it's let's fix the plot range. This plot range, go out to 4, say. So this is the lambda equals 0 case. The horizontal coordinate going from 1 to 2. The vertical coordinate going from 0 to pi. If you were going to label the axes when lambda is 0, you'd want to label this r and theta, not x and y. On the other hand, when lambda is 1, I purposely went really fast there. When lambda is 1, here's the set, and now you want to think of this as an x-axis and this is a y-axis. And this is the transformed rectangle in the xy plane. It's the geometric effect of capital G. It's called the image of the original rectangle under capital G. We could also call it the range. What happens in between? What happens in between is just for fun. To imagine the geometric effect of what's going on here, this is one way to imagine it. Okay? Is that literally what's going on? No, it's not actually. Let's put the performance goal in here. That's not what's literally going on. Because the intermediate values of lambda don't have any meaning for us. There are some contexts where you would want to give meaning to the intermediate values of lambda. But for us, what's important is lambda equals 0 and lambda equals 1. But this is just so much fun, I can't resist doing it. Okay? It's nice. It's a nice way to imagine the geometric effect of this transformation, of this mapping. Make sure you read section 15.6. You'll definitely get benefit out of it. Coming back to class next Monday after Thanksgiving, we'll talk about this topic some more. We'll talk about what happens when this Jacobian determinant is not a constant. Why is it a local magnification factor? And definitely, if you read it ahead of time, it'll be beneficial for you. There are completion problems to work on, but you don't have to turn them in next Monday. You should work on them as much as you have time for. Okay? Have a good Thanksgiving.